Hello everyone, welcome to Abhi online classes. Today we shall discuss Cauchy-Maclaurin's integral test in infinite series. Let f of x be a non-negative monotonically decreasing integrable function on closed one open infinity. Then the series sigma n is equal to 1 to infinity f of n and the improper integral 1 to infinity f of x dx, they both converge or diverge together. That is, the series sigma f of n converges or diverges according as the integral 1 to infinity f of x dx tends to a finite limit or diverges to infinity as n tends to infinity. That is, these two either converge together or diverge together. This sigma f of n converges if this integral tends to a finite limit as n tends to infinity. This sigma f of n diverges if the integral 1 to infinity f of x dx diverges to infinity as n tends to infinity. Now we will see one problem. Test the convergence of the series sigma 1 by n square plus 1. Now we take f of x is equal to 1 by x square plus 1 for all x belongs to interval closed one open infinity. Clearly this f of x is positive, that is greater than 0. The one condition is f of x should be non-negative, that is it is either greater than 0 or equal to 0. So the first condition is f of x should be positive, and the second condition is f of x must monotonically a decreasing integrable function. So here also f of x is monotonically decreasing in this interval. Now we find integral 1 to n f of x dx equal to integral 1 to n 1 by f of x means 1 by x square plus 1 dx. Integral 1 by 1 plus x square is tan inverse x. Now we apply limits. First upper limit tan inverse n minus, now we substitute lower limit in place of x, tan inverse 1. Tan inverse n minus tan inverse 1 is pi by 4. Now apply limit n tends to infinity on both sides. Limit n tends to infinity, integral 1 to n f of x dx is equal to limit n tends to infinity. Previously we have seen integral value is tan inverse n minus pi by 4. Now putting n is equal to infinity, tan inverse infinity minus limit of constant is constant. Tan inverse infinity pi by 2 minus pi by 4. Pi by 2 minus pi by 4 gives pi by 4. Therefore, integral 1 to infinity f of x dx, that means letting n tends to infinity, integral 1 to infinity f of x dx converges to a finite limit, that is pi by 4. So according to the Cauchy's-Maclaurin's integral test, if this integral converges to a finite limit, sigma f of n, this series also converges. Sigma f of n is equal to sigma 1 by n square plus 1 also converges. Now we will see one more problem. Test the convergence of the series sigma 1 by n into log n. Here f of x is 1 by x into log x. So clearly this x belongs to close to open infinity, because for x is equal to 1, log 1 value is 0. 1 by log 1, and that means 1 by 0 is infinity. F of x will be undefined. So f of x must be defined only for x belongs to close to open infinity. Clearly f of x is greater than 0 and monotonically decreasing in this interval. Both the conditions of Maclaurin's are satisfied. Now we take integral 2 to n f of x dx is equal to integral 2 to n 1 by x into log x dx. Now we use here integral 1 by x into log x dx, we write it as integral 1 by x by log x dx. It is in the form of integral f dash x by f of x. We know this formula. Integral f dash x by f of x is log of f of x. Here f of x is log x, so we got log of log x. So on integrating this function, 1 by x log x gives log of log x. Now putting upper and lower limits, log of log n minus log of log 2. Apply limit n tends to infinity on both sides. Limit n tends to infinity, integral 2 to n f of x dx is equal to, on applying n tends to infinity limit, log of log n tends to infinity minus log of log 2. This is a constant. Limit of constant is constant itself. Infinity minus something also gives infinity. So now applying n tends to infinity, this integral 2 to infinity f of x dx gives infinity. That is, it is diverging to infinity. Therefore, by Cauchy's-Maclaurin's test, sigma f of n, the given series also diverges. Like this, by Cauchy's-Maclaurin test, we can test the convergence or divergence of the series. Hope you understood this class. Thank you.